Okay, we have a good one here today from the UK integration bee 2024, number 17. We've got the integral from 0 to infinity of e to the minus x times all this stuff over x squared dx. Okay, this is a problem that I already did a few days back, but I got some interesting suggestions in the comments. For this one, I had a suggestion from Samir that we still use Feynman's trick on this, but we do it parameterizing it in a different way. In the first video, what I did is I created a parameter on the e to the minus x. What he did instead, which is really interesting, is he made a parameter on this 23. So how we'll do this is we'll create a variable s and we'll rewrite this integral. So then now we're just going to have e minus x, but the 23 is what we're going to call our s. So we're going to have sx minus 1 plus e minus sx all over x squared dx. So for this to be equal to our original problem, we want to say this here is going to be just f of 23. And with Feynman's trick, we're going to want another value where we can evaluate this. Well, it turns out the thing that I think is going to work is if you look at s equal to 0, you plug a 0 in here, that goes away. You plug a 0 here, this becomes 1. So what's going to happen is when s is 0, it's going to zero out the integral, so we can say f at 0 equals 0, and we'll come back and use this later. So next what we want to do is I want to get my derivative using Feynman's trick. And what we want to do on this is we want to differentiate inside the integral as a partial with respect to s. Now, a lot of stuff here is constants. Like this whole part here, this is a constant with respect to s. So let's kind of just bring that out front as a constant here. And we'll differentiate on all this other stuff. Sx minus 1 plus e minus sx dx. Well, when you differentiate this with respect to s, what happens is here, the derivative of sx is just going to be an x. Derivative minus 1 is 0. Derivative of this part, we get e minus sx, and then a minus x is going to pop out, so we'll write it as minus x e minus sx. So now we'll use this and we'll put it back together. When I do this, we can do a few things here. So everything here, we have x, it's all over x squared. The e minus x I can distribute in, and actually let's factor an x out because we've got x in common here and here. So if I factor an x out front, distribute the e minus x in, then we're just going to have e minus x minus, here we've got the same base, e minus x times e minus sx. I can write that as e minus s plus 1 times x. But now that I have this x factored out, we've got it in common here. So what I can do is just cancel this x here with one of these. And then what we've got right here, this is exactly in the right form for Frullani's integral. Okay, so we've seen this formula before on the channel, and it's kind of a crazy formula to think that with something this complicated, we can basically go right to a solution. What's going to happen is we have this set up in our problem. Okay, we've got the x in the denominator, we got the right bounds. The thing is setting it up where we've got the same function here and here with just a different input. So for this to work, we're saying our f of x value is going to be e minus x. So then this piece right here is going to be our f inputting a of x, where a is just 1, so it's really just the same as our f of x. And then this second piece, we're going to call this our fb of x, where the b value is just this input, s plus 1. So just using this formula over here to the right, we can go ahead and just go and calculate this. The problem you can run into sometimes is you need it to be defined at infinity and 0, but we're not going to have any problems here. So first of all, just looking what happens for f at infinity. Think about this as a limit. So if you take the limit as x is approaching infinity, this first piece is going to 0. Then f of 0, we can just plug in e to the 0 is just 1. Then for the next part, we want natural log of a over b, so that's just going to be 1 over s plus 1. But simplifying a little bit, this part right here is just a minus 1. We can bring it into the exponent and use it to flip this fraction. And so what we get for our f prime s value is just going to be natural log s plus 1. Okay, so now that we have our f prime s value, the next step is going to be to backtrack because we're going to need to find out what our f of s is. And then finally we plug in 23 to get to our solution. Let me clean up the board and we'll continue. Okay, now from here, in order to get back to our f of s, we have a derivative. Let's just integrate it on both sides, but we're integrating with respect to s now. For this one, we'll just use the formula with our input just being s plus 1. Because if we have the integral of natural log x dx, our formula for this is x ln x minus x plus c. So I'll use this and just kind of plug in s plus 1. So we get s plus 1 natural log s plus 1 minus, distributed into this, we get minus s minus 1 plus c. But minus 1 is just a constant, so let's absorb that into this constant that we need to find. And so now we've got our expression for f of s. The only trouble is we don't like having a constant in it. That's where we can use this condition that we found earlier. So what we want to do is look at this thing at f of 0 as we determine the value that's going to be 0. So we plug in. Here we're going to have, this piece is going to be a 1. So we're going to have 1 ln 1 minus 0 plus c equals 0. Well, ln 1, that's 0. This is 0. That's 0. Everything's 0. So what we can say is c also needs to be 0. So let's make this thing here go away and get rid of all this junk that we don't need. And so now we have the expression that we want to use to finish this thing off. All we need to do is we need to remember, going back to our original problem, the s value here was just 23. So we just need to plug in. So to find our f value at 23, we're going to get, plugging in here, we're going to get 24 times natural log 24 minus 23, and that's it. Okay, so there you go. Really nice alternative method from Samir in the comments. Thanks everyone for watching. Have a good day.